If all motion ceases and there's no vitality left, the engine reaches its final state, the state of equilibrium. From a scientific perspective, then, what's the picture?
In this molecular dynamics calculation, each pair of atoms is programmed to interact with a realistic interatomic force.
So then what really happens when a warm body is brought into contact with a cold one? Thermal energy spreads from warm to cold until both bodies reach the same temperature. This is the state of thermal equilibrium. At first glance, thermal equilibrium seems different from the mechanical idea of stable equilibrium, which keeps a body safe from falling. But take a closer look. When a falling body hits the ground, each bounce is smaller than the last. Why? Because the kinetic energy of the body as a whole becomes transformed into the chaotic motions of the atoms that compose it. And that process is very similar to heat flowing into a cold body, and the end result is the same. All of the available energy eventually becomes shared out as kinetic and potential energy of random motions of all the atoms. Therefore, although the idea of equilibrium seems the ultimate in peace and serenity, that view hides the seething motion of the atoms within. So understanding equilibrium is a matter of perspective, of seeing within, and of seeing beyond. Because equilibrium is a state in which all temperatures are equal, it's a place where no machines operate, no geysers spray, no volcanoes erupt, no water falls. No big engines want to do any work, and no little engines can. Everywhere, nature seems impelled toward the state of equilibrium. Hot bodies and cold ones striving toward the same temperature, and falling bodies turning perfectly good work into useless heat. From the physicist's point of view, when nature tends to behave in such a universal fashion, there must be a scientific explanation, and there is. The explanation began as an idea, of course, an idea for the construction of a better steam engine.
There was a young man named Carnot, whose logic was able to show, for a work source proficient, there's none so efficient as an engine that simply won't go.
C.D. Carnot's greatest ideas never worked, and in the real world probably never will. Yet he had the desire to create an engine as perfect as nature would permit, and the logic to come pretty close.
Given a difference in temperature, a high temperature, T sub I, and a low temperature, T sub O, Carnot designed a perfect abstraction. The Carnot engine takes in heat, Q sub I, at the high temperature, turns some of it into work, W, and expels the rest, Q sub O, as heat at the lower temperature.
Because the Carnot cycle could run just as well in reverse, it was the picture of the ideal engine.